Hey everybody, this is the final lecture for Chem 103. Sorry for the technical difficulties. The internet just had to come for me, so I couldn't be great. But there isn't a whole lot of content here, and it should be relatively easy compared to Chapter 9. So I'm grateful that we got through Chapter 9 without any issues. There were some questions about, Alex homework, the final, exam 4. For Alex homework, you have until May 6th, the end of May 6th, to get done what you can get done. So however much you get done, that's what your homework grade will be. If you have specific questions about, something that happened, internet, whatnot, email me and I'll see what we can do. Your exam is on Thursday of next week, so that's the 30th. We're going to have a problem-solving session on Tuesday. So I'm going to post a practice exam for you to do. If you post your answers before class on Tuesday of next week, then you will get your 5 points extra credit for exam 4. I will put out an announcement and an email when that is posted. I'll do the same thing for the final exam. We don't have class between exam 4 and the final, but I will give you a practice exam and I will still hold office hours during the week of exams. So if you have questions, you can always stop by office hours or send me an email. If you have any other questions about logistics for the rest of the semester, how grades are calculated, anything like that, let me know. Without further ado, we'll talk about gases and some gas laws, and that'll be it. So let's first talk about the properties of gases. There are several properties we need to address. The first is that gases have a variable shape and volume. I'm going to switch over to black here because red just seems a little too intimidating. So the gas takes the shape of its container. If you have a balloon, which I ain't the best artist, you can blow up that balloon to be whatever size you want. You can have a smaller balloon, you can have a big old balloon. The gas that you fill it with you're going to have variable shapes, okay? So think about that. Gases expand uniformly. So whenever you have let's say that you have a container of gas and you're opening that up in a room, that gas will expand uniformly across the room. Gases also compress uniformly. So say you were able to recapture all that gas. You're going to recapture that gas and fill the volume of whatever container. So just like it'll constantly expand, it'll also, when you compress the gas into something smaller, you'll fit all that gas back into that container and it will fill that container. Gases have a low density. So the density of air is about 0.001 grams per milliliter in comparison to water, which is 1 gram per milliliter. So air is much, much less dense than water, and air is a combination, it's a mixture of gases. The last one is that gases mix uniformly with other gases. So if you think about air, you don't have a pocket that's really rich of oxygen and then one piece of the globe that has a lot of nitrogen. The air is the same, okay? Now we may add stuff to the air because we pollute, but we're just talking about the air in and of itself in the atmosphere. It's the same mixture and it's the same percentage everywhere. Just like air, if you mix gases in a sealed container, they're going to mix so that it's just a homogeneous mixture, okay? You're not going to have a pocket of one gas over here and one gas over there. They're not bougie. They mix together. Gases exert pressure on the walls of the container that they're in. And that pressure is the result of gas molecules constantly moving around. So if you think about a room full of toddlers that have just been given, you know, a bag full of Halloween candy, which I would never do. That's a death wish. But say someone did that, okay? They would be bouncing off the walls, literally, perhaps even the ceiling. That's what gases do too. They're constantly moving, they're striking into things and bouncing off of the walls, they're bouncing off of other gas molecules. And at a higher temperature, you're going to have molecules moving more quickly, striking the walls more often. So you're going to have more force and an increase in pressure. So that's what's shown here on the right. And these red arrows mean that the temperature is higher. So these gas molecules are moving around a lot faster. And the pressure gauge is way over here on the right. For B, with the lower temperature, you see there's fewer arrows and they're blue. So it's a cooler temperature. The molecules are moving, they're bumping into the walls, they're bumping into each other, but the pressure is not as high. And you can see that the reading for the pressure is on the far left, so it's much lower than the gas at a higher temperature. So the take home here is that gas pressure is the result of the gas molecules moving around constantly and striking the walls of the container. Atmospheric pressure is a special type of pressure, and this is the result of the air molecules pressing down on the environment. And there is a researcher, Evangelista Torricelli, who invented the barometer, and that measures atmospheric pressure. So what you have is liquid mercury in some kind of a container, and it's also in a glass tube. The air pressure pushes down on the mercury. And mercury is pretty dense stuff, okay? It's going to push down on the mercury and cause the mercury in the container to move up the glass tube. And the length or the height of the mercury is what you can measure. So you'll see millimeters of mercury. That's literally what you're measuring. You're measuring the height of the mercury in the barometer. The other measurement you'll see is the torr. The torr is the same thing as millimeters of mercury. It's just a unit that's named for Torricelli, the person who invented the barometer. 1 atmosphere, which is abbreviated ATM, is equal to 29.9 inches of mercury, which is equal to 760 torr, which is equal to 760 millimeters of mercury. Okay, so these are all of the pressure units that you may see. You'll get these on the exam. I'm not going to make you memorize them, but you will need to be able to convert between atmospheres and torr or inches of mercury. So this is a table that gives you the information that I just gave you. And I want to note here that these pressures are exact. Okay? We're really just going to deal with atmosphere, millimeters of mercury, and torr. I'm going to show you an example using inches of mercury, but the 3 that I put a star by, those are the 3 measurements that you're really going to need to be concerned with. So going back and forth between atmospheres and torr or millimeters of mercury. So here's an example of how to do a conversion. So the barometric pressure is 26.2 inches of mercury. What is the barometric pressure in atmospheres? So this is a conversion question. We have 26.2 inches of mercury. And the question is asking, How many atmospheres is that? Well, what you would get on the exam is something that has, all of the one atmosphere is equal to, 29.9 inches of mercury, which is equal to torr and this and that. The one that we need is that one atmosphere is equal to 29.9 inches of mercury. This is your unit equation. They're coming back, y'all. We did this in chapter 2. Unit equations are here to stay. We were using them in chapter 9. We're still using them in chapter 10. This is our unit equation. Now we need a unit factor that's going to help us convert from inches of mercury to atmospheres. What we want is atmospheres, so that should go on the top. And what we're trying to get rid of is the inches of mercury. So we'll put that on the bottom. So that's our unit factor. To solve the problem, we're going to take our given information, which is 26.2 inches of mercury, and multiply by our unit factor. So when you put this into your calculator, you should be doing 26.2 divided by 29.9. We should report our answer in 3 significant figures because there are 3 sig figs in our given information. Your calculator will give you more than that, but don't believe it. Okay, give me 3 sig figs. And don't forget your units. Should be in atmospheres. That's the whole purpose of doing all of this, so that we can actually know what units we're doing. You're getting rid of the inches of mercury so that you have atmospheres. So don't give me naked numbers. Naked numbers are cold and lonely. Give me a unit. So we talked about the properties of gases. We talked about what gas pressure is, that it's gas molecules striking the walls of the container. There are some variables that affect gas pressure. The 3 we're going to talk about: the volume of the container, the temperature of the gas, and the number of molecules of gas in the container, so the amount of gas present. We're not really going to get to talk much about this third one. We'll address it, but we're not going to cover the ideal gas law, unfortunately, which would cover the number of molecules and how that affects the pressure and things like that. The first law that we're going to look at is Boyles Law. And so what he looks at is pressure and volume. So we're looking at pressure and volume, and we're saying temperature and amount of gas stays constant. So the pressure and volume are variable. If you keep the temperature and the amount of gas constant, the relationship between pressure and volume is inversely proportional. So what that means is if you increase your pressure, you're going to decrease your volume. So if you think about it, if you have a container with gas and you are able to shrink that container, those gas molecules are going to be a lot closer together, and you're going to be able to strike the walls much more frequently because there's less room. If you took toddlers and put them out in the backyard with all that Halloween candy and they're sugared up, they can run all around and maybe they won't bump into each other as often. They'll still bump into each other and everything else, but maybe not as often. You take all of those children and put them into a small room, the pressure's gonna go up. They're gonna be bouncing off every surface, and so will the gas. I'll show you how we can use the equation that was derived from this relationship. Okay, so our equation is the initial pressure and volume, which is P1 and V1. So these are our initial conditions. When you multiply the pressure and the volume of the initial condition, it should be the same as when you multiply the final condition, the pressure and the volume together. I'll show you how that works. A sample of 3.50 liters of methane gas has a pressure of 1,550 millimeters of mercury. We want to know what the final pressure is going to be if the volume is changed to 7 liters. The first thing you want to identify is what kind of information you have. Okay, 3.50 liters, that's a volume. And since we're talking about the initial, we're going to give it a 1, okay? It's part of the initial condition. That gas with that volume has a pressure of 1,550 millimeters of mercury. Millimeters of mercury is a pressure, so we're going to call that P1. What is the final pressure if the volume changes to 7 liters? That gives us a clue that the 7 liters is part of our final condition, and liters is a volume. So let's write out what we have. When you're in an exam setting, you're not going to know which gas law you're supposed to use until you read the question and see what you have. What I didn't mention is that it said final pressure here, so that's going to be your P2. Okay, we don't know that. But our P1 from the problem is 1,550 millimeters of mercury. V1 is 3.50 liters, and V2 is 7 liters. Our P2 is going to be in the same unit as our initial pressure, so you can go ahead and write millimeters of mercury for that so you don't forget. Again, naked numbers are cold and lonely. Don't do that to the numbers. They've served you so well. Now that we see what we have, we've got pressures and volumes, we know that we're dealing with Boyles Law. And Boyles Law, we use the equation P1V1 is equal to P2V2. What I like to do is circle the variable that I need to solve for. So in this case, the question is asking about what is P2, the final pressure. So that's what I need to isolate. To do that, I'm going to divide by V2 on both sides. When I rearrange and clean it up a little bit, we get that P2 is equal to, I was excited, I started writing a V already. So V1 P1 over V2. The other way to write this would be P1 times V1 over V2. This V1 over V2 you will sometimes see referred to as a volume factor. I don't believe you have to do chapter 10 for your ALEKS homework. I'm pretty sure that I took that off. But if you take other chemistry courses beyond 103, then you may encounter the volume factor the temperature factor and some other things that I'm going to introduce but not hold you accountable for. Okay? I just at least want you to have seen it, and maybe it'll register in your brain at some point that, hey, Dr. Hefner talked about that. All right. So let's put some numbers in here. P1 was 1,550 millimeters of mercury. Our V1 was 3.50 liters, and V2 is 7 liters. When you do all that math, what you should get is 775 millimeters of mercury. Now let's do a check. What happened with this was that we have our volume increasing. It increased from 3.5 liters to 7 liters. When the volume increases, that means that our pressure should decrease. Whatever happens to the volume, the opposite happens to the pressure because they're inversely proportional. When you look at your answer, P2 is 775 millimeters of mercury. That is less than the pressure that it started at. So that makes sense. Always make sure to do that mental math check to make sure that your answer aligns with the logic of how gases behave. The next gas law that we're going to talk about is Charles's law. So Jacques Charles, he discovered that the volume of a gas is directly proportional to the temperature in Kelvin. I'm going to underline that and circle it. Kelvin, okay? Kelvin, Kelvin, Kelvin. K, Kelvin. It does not work with degrees Celsius. What that means is if you increase your volume, you're also going to increase your temperature. The same is true if you decrease your volume, you're going to decrease your temperature. So the same thing happens to the volume as happens to the temperature. To use Charles's law, which is V1 over T1 is equal to V2 over T2, the first thing you're going to want to do is cross multiply. So you're going to multiply V1 by T2, and you're going to say that's equal to V2 times T1. Mind your subscripts. When you're putting this in and you're putting your variables in the proper places, make sure that you're putting V1 where V1 goes, T1 where T1 goes. Okay? This is one of those little details that can lead you astray. Once you do your cross multiplication, then you can figure out, okay, I'm solving for, let's say V2. You circle it, you rearrange the equation so that you have V2 on one side and everything else on the other side. But before you do anything else, you're going to want to cross multiply so that you get this, okay? Now I'll show you how to use it in a problem. But first I'm going to show you a picture. So if you have a balloon at room temperature and you cool it with liquid nitrogen, which you probably don't have liquid nitrogen just hanging out in your house, you shouldn't. But if you do, and you just happen to drip a little onto the balloon, you'll see that the volume decreases. And liquid nitrogen is really, really cold. So you're decreasing the temperature of the gas in the balloon, and you're also decreasing the volume. So those gas molecules don't have the same kind of energy that they did before because they're colder now. So they're not going to be taking up as much volume. They're going to move around a lot less, and they're not going to be able to hold the shape of the original size of the balloon. Now we'll do a problem. We have a helium balloon with a volume of 132 liters. We heat the balloon from 20 degrees Celsius to 40 degrees Celsius. What is the final volume at constant pressure? You'll notice that with these gas laws, we're only looking at two variables. So if we're looking at volume and temperature, that means that the pressure and the amount of gas is going to stay the same. So let's identify what we've got. We've got a volume, and we'll call that V1, and it's heated from 20 degrees Celsius that tells us it's initial, so we'll call that T1, to 40 degrees Celsius. Sounds like T2 to me. That's the final, right? What is the final volume, which we'll call V2, at constant pressure? So when you're doing these problems, again, you're identifying the kind of information that you have and writing it out. That will illuminate which gas law to use. We have 132 liters as our V1. Our T1 is 20 degrees Celsius. Our T2 is 40 degrees Celsius. And our V2, no clue, but it should be something in liters. Now, look at our T1 and T2. They're in Celsius. Celsius, bad. We need to convert that to Kelvin. Again, we are digging back to chapter 2. To convert Celsius to Kelvin, you have to add 273. And that gives you 293 Kelvin for T1. And 313 Kelvin for T2. So always, always, always convert degrees Celsius to Kelvin for gas law problems. Since we've only got volumes and temperatures, that means that we're dealing with Charles's law. Charles's law states that the volume and the temperature are directly proportional. But as the equation is right now, we can't use it. Cross multiply. V1 times T2 is equal to V2 times T1. That makes it a lot easier to handle. We're looking for V2. The question asks, what is the final volume? So we need to isolate V2 on one side and get everything else on the other. To do that, we're going to divide by T1. Clean it up a little bit. V2 is equal to V1 times T2 over T1. This is called your temperature factor. My A disappeared. Okay. Again, you don't need to know that terminology, but it may crop up again if you have to take another chemistry course after this one. So I want you to be as prepared as possible. When we fill in the numbers from the problem, our V1 is 132 liters, and we're going to multiply that by our T2 on the top, which is 313 Kelvin, and divide that by 293 Kelvin. When you do that, you should get 141 liters as your final answer. Let's do the check though. We started with an initial volume of 132 liters. Our temperature went from 20 degrees to 40 degrees, which means that our temperature increased. Charles's law says that whatever happens to the temperature, same thing is going to happen to the volume. So our volume should increase too. Did our volume increase? Yep. Always do that check. It may seem really simple, but it will help you, because if you did something wonky and let's say you put T1 over T2, you're not going to get the same answer. So if you do the mental check and know that your volume should increase, you'll at least know to go back and recheck your math. You may not know exactly what you did wrong, but you at least know my answer right here isn't right. So take the extra minute and do it, for me. The final law that we're going to cover is Gay-Lussac's law. So Joseph Gay-Lussac, he did a lot of work with gases, and we already talked a little bit about him in terms of molar volume in chapter 8. And we also talked about volume to volume stoichiometry problems in chapter 9. So he's dabbled a bit with the gases, okay? What he looked at was pressure and temperature. Pressure and temperature have a direct relationship. When you increase the pressure, you also increase the temperature. And that's, again, assuming that volume and amount of gas is constant. Once more, the temperature has to be in Kelvin. Whenever you're dealing with gas laws, you have to deal in Kelvin. Celsius does not work here. It must be Kelvin, the absolute temperature scale. You'll notice that this equation looks very similar to Charles's law. That's because it's a similar relationship, a directly proportional relationship. Which means we're going to do the same thing to make this workable. You cross multiply to get P1 times T2 is equal to P2 times T1. Once you do that, then you can use the equation to solve for whichever variable you're looking for. I'll show you how to do that in yet another problem. A steel container of nitrous oxide at 10.4 atmospheres is cooled from 33 degrees Celsius to negative 28 degrees Celsius. What is the final volume at constant volume? Oh, that should say, what is the final pressure? See? I ain't perfect. I must have been tired. What's the final pressure? The sad thing is, I went through and solved all these problems. I read it, didn't see it, not till just now. Alright, anyway, we're looking for the final pressure at constant volume. A steel container, that will kind of clue you in because it's not going to expand or contract like something else would. Different materials might, like a balloon, let's say. As always, the first step is to go through and identify the kind of information that we're given. 10.4 atmospheres, that is a pressure. So we'll call that our P1. We're given the initial conditions. And it says that that gas is cooled from 33 degrees, so this must be our initial temperature, to negative 28 degrees Celsius. Sounds like a final temperature to me. What is the final pressure, P2, at constant volume? So you're going to go ahead and write out everything that you know, and that will tell you what gas law you have. You have 10.4 atmospheres, 33 degrees Celsius, minus 28 degrees Celsius. And P2, no idea, but We know it'll be something in atmospheres because that's what our initial pressure was given in. Because we only have pressures and temperatures, this clues us in that we have to use Gay-Lussac's law. You cross multiply, and then you identify which variable it is that you need. We're looking for a final pressure, so I circled P2. To rearrange, you're going to divide by T1 on both sides. Clean that bad boy up, and we have P2 is equal to P1 times T2 over T1. So that's the temperature factor, just like I said before. Fill in the numbers that you have. 10.4 atmospheres for P1, and then for T2 and T1, we need to convert. 33 degrees Celsius, that's going to be 306 Kelvin. And remember, just add 273. Negative 28 degrees Celsius, you're taking 273 and adding a negative number, so you're basically subtracting. You're doing 273 minus 28, and you should get 245 Kelvin. Fill in those numbers now that you have your temperatures in Kelvin. T2 is 245, T1 306. Before we do the math, let's do our check to see whether or not our pressure should increase or decrease. Our temperature, we started at 33 degrees and we went down to minus 28. That means that our pressure should also decrease. So we're looking for something that's going to be less than 10.4 atmospheres. When you work out the math, you should get 8.34 atmospheres, which is absolutely less than 10.4. That's all that I have for the gas laws. I didn't want to overload you by doing, these three gas laws. There's the combined gas law, there's the ideal gas law, there's taking the ideal gas law and combining that with stoichiometry problems, and we simply didn't have the time to cover that sufficiently. So I at least wanted to give you a taste of the gas laws and give you a little bit of the easier math to do so that you understand the properties of gases and the different variables that affect the pressure of a gas. This is it. I'm not going to spring anything else on you. There's no assignment for Chapter 10. What I want you to do is work on the exam review that I've posted. Work on that, submit it before Tuesday's class. So 10:30 a.m. Tuesday, April 28th. Have it in by then. Any submissions after that, not accepted. Make sure it's in the right format. So make sure it's a PDF, PNG, JPEG, something like that, or Word doc. Don't give me anything that I can't read, because I'm going to be going over the answers in Tuesday's class. And I'm not going to have time to go through and grade everybody's stuff, or at least take a look at it before class. So if you have questions on anything, as always, reach out via email. I'll have office hours. We have class on Tuesday. So let me know what you need, and hopefully this lecture was self-explanatory enough that you'll be able to get it. Have a good one, you guys.